For the next few weeks, we're going to be working on a project that ties together all the things that we've covered up to this point in the semester. This project is known as an oscillator or as an astable multivibrator. It's going to involve transistors, capacitors, resistors, diodes, pretty much everything we've talked about up to this point. So let's go ahead and get started on this. It'll be a 3-week project. The first week we're going to talk about the theory and understand how this circuit works. We're going to simulate it and demonstrate how it works in simulation, and then we'll breadboard it up into a prototype and show that with discrete devices that it does exactly what we think it's going to do, and we'll be able to look at it on the oscilloscope. The second week we'll lay out the circuit to prepare for for getting a printed circuit board made. And then we'll get the circuit boards, and on the third week we will go ahead and solder up the circuit board and then verify that the completed final project is working the way it's supposed to work. This is the circuit we're going to be working with, and let's just take a second to look at it and identify the different parts of it. First of all, you'll notice that it's going to be a DC, or at least the source is DC. We're going to be using a 9-volt battery. There are 4 resistors, a couple of transistors, and a couple of capacitors. Now notice, and by the way, these diodes right here are LEDs, and when this circuit is operating, the LEDs flash. One will be on, and then the other one is on, and then the other one, and it just goes back and forth flashing those lights. And it's all done automatically with this circuit. So let's just look at, first of all, the topography of the circuit. You'll notice that these two transistors, in fact, let's even back up. You'll notice that this circuit really consists of 2 circuits of the exact same type. There's an NPN transistor, a capacitor, and these 2 resistors. There's another transistor, a capacitor, and these 2 resistors. So really what we have is the same circuit duplicated or replicated twice. And as we're going to see that this part of the circuit here works just like this part of the circuit does over here, only that they work at different times. You'll also notice that the left part of the circuit is connected from this point here to the base of Q2. And similarly, the right part of this circuit is connected through this line here to the base of Q1. This type of cross-connecting is sometimes referred to as a cross-coupled circuit, and it's also we'll sometimes refer to it as there being feedback. That what's happening on this side of the circuit is being fed back to here, and what's happening on this side of the circuit is being fed back to here. So what happens is that this circuit here, and specifically this voltage here, is going to control the voltage on the base of this transistor. And similarly, this voltage here is going to control the voltage on the base of this transistor. Now you'll recall that transistors, one of the things that transistors can do is switch. They are electrically controlled switches. And these transistors are going to be working in that state. The transistors will either be on or off, and as we're going to see in just a minute, when one of them is on, the other one is off, and when this one is on, this one will be off. And the thing that's going to control them, as you know, is the voltage at the bases. When the voltage is about 0.7 of a volt here, this transistor will be conducting, and the voltage across that transistor will be the saturation voltage, which is about 0.1 or 0.2 volts. When this transistor is on, the voltage here will be about 0.7 of a volt, and the voltage across the transistor will be the saturation voltage, again of about 0.1 or 0.2 volts. If the base voltage is significantly less than 0.7 of a volt, the transistor will be off. There will be no current flowing through it. If the base voltage gets up to about 0.7 of a volt, it then turns on the transistor and current does flow through it, and again the voltage across it will be about 0.7 of a volt. or voltage across it will be about 0.2 of a volt, 1 to 0.2 of a volt. When this transistor is on, meaning that the base voltage is 0.7 of a volt, when this transistor is on, then current is flowing through it. We will also have then a path for current to go through the LED. The LED is going to glow, going through R2 and on down. It will also under those circumstances, with this voltage here being about 0.1 or 0.2 volts, and this voltage here being 9 volts, there will be a path through R4, through the capacitor, to charge the capacitor through the transistor. So let's repeat that. When this transistor is on, this voltage here is going to be about 0.1. Let's just say it's going to be 0.2 volts. But our saturation voltage is 0.2 of a volt. The current then will be flowing through the diode. The diode will be forward biased because this voltage here will be lower than this voltage up here. Current will be flowing through it, through R2, on through the transistor. At the same time, with this voltage here being 0.2 of a volt and this voltage here being 9 volts, there will be current flowing through R4, charging the capacitor, and then flowing through Q2 also. When this is on, this one is off. There will be no current flowing through the transistor. And with no place for current to flow, the voltage on the capacitor, VC1, reference plus to minus, will be relatively stable at that point. And we'll see here in just a minute what that VC1 voltage will be when this transistor is off. When you analyze circuits like this with this cross-coupling, this feedback, you just kind of have to assume a certain state and then see what happens given the assumptions that you've got. And we're going to follow those assumptions on along, and we'll see that it then causes some transitions to take place. But again, let's start off by just assuming that Q1 is on, transistor 1 is conducting, and transistor 2 is not conducting. Transistor 2, or Q2, is off. In that state with Q1 on, that tells us then that the voltage at the base right here, what I've referred to as V of Q1 at the base, is going to be about 0.7 of a volt. Just that forward biased PN junction here, turning that on. And the voltage across here then is going to be the saturation voltage of 0.2 of a volt. Now at this point, we don't really know what the voltage is here, but we're just assuming that it's off, which means the voltage here is going to be something less than 0.7 of a volt, and there will not be current going through this transistor. With no current going through this transistor, there'll be no current going through this resistor, and V, the collector voltage here, VQ2 for a Q2 transistor at the collector, is going to be pulled up toward 9 volts. It's not obvious that it's going to get all the way to 9 volts because you've got a diode here and some other things. But the point is that there is no current going through here, so this voltage is going to be pulled up by this resistor up towards 9 volts. Again, we're not just sure what this voltage here is. Now, let's just assume that it just switched to that state, where it just turned to this voltage here being 0.7 of a volt, this voltage here being 0.2 of a volt, and this voltage up around, well, let's say it's up at 9 volts. Now, we've got 9 volts here, we have 0.7 of a volt here, so as quickly as possible, that capacitor C2 will have charged up to the 9 volts here, the 0.7 of a volt here. The voltage on C2 will have charged up to about 8.3 volts. So plus to minus 8.3 volts on that capacitor. On the other side, we've got 0.2 of a volt right here. We've got 9 volts here. And so R3, or rather C1, is charging through R3 at a rate controlled by the time constant R3 times C1. And it will be charging up to a voltage across here, when it would, if it were to be able to get there, it would be charging up to somewhere around 9 volts minus 0.2 volts, so up around 8.8 volts. But something happens before it gets anywhere near that high. You'll notice that this voltage right here, which is equal to the 2/10 of the volts, 2/10 of a volt here, plus whatever the capacitor is charged up to, will, or that point is connected to the base of Q2. So as this voltage starts to grow, the voltage on the base of Q2 is also growing. And this voltage will continue to grow until the voltage here gets to be 7/10 of a volt. When this voltage here gets to be 7/10 of a volt, it turns Q2 on. It had been off, it's now turned on. With Q2 being turned on, it gives us a voltage across this transistor of about 0.2 volts. It had been pulled up there around 9 volts, or just a little less than 9 volts. But now when the transistor turns on, it's like closing this switch. Here's my ground. This is 0 volts. I've got 2/10 of a volt saturation across the transistor. That makes this voltage here, which had been up around 9 volts, now somewhere around 0.2 volts here. Now, you don't change the voltage on the capacitor instantaneously. This capacitor was charged up to about 8.3 volts, positive to negative. So here we are at 0.2 volts, instantaneously changing. The capacitor still has an 8.3 volt charge on it. So the voltage here at this point then gets suddenly pulled down. It had been at 9 plus to minus 8.3 gave us the 7/10 of a volt. Now instead of starting at 9 here, we're starting at 0.2. 0.2 plus to minus, dropping 8.3 volts, pushes the base voltage of Q1 down to about, well, somewhere on the order of negative 8 volts. Maybe 8.1, 8.2 volts. If we use these numbers, this is positive 0.2 minus 8.3. This would be down at negative 8.1 volts. Well, a negative voltage on the base of this transistor is going to shut this transistor off very quickly. And now instead of this being 7/10 of a volt, we don't really know exactly what this voltage is. We just know that this isn't switched on, or that this isn't conducting. Let's go back and see what happened then. When this voltage here climbed up to 7/10 of a volt, it turned on this transistor, pulled this voltage down here to 0.2 volts, which pulled this voltage down here to about negative 8.1 volts, which then turned this transistor off so that there is now no current flowing through that transistor. This transistor turning on turned this transistor off. And that's our assumption initially, that they wouldn't both be on, but rather one or the other would be on, but not both. We can see that when this one turns on, it automatically turns this one off. Now we're in this new state, this new switched state, where Q1 is off, Q2 is on. With Q1 off, we've already seen that the voltage here is about negative 8.1 volts. And this voltage here, we don't know exactly where it is, but because there's no current flowing through here, there'll be no voltage dropped across here, no substantive voltage drop across here, and the voltage here will be pulled up to on the order of 9 volts. So let's just say that this now has gone from being 0.2 volts on up to 9 volts. And this voltage here, where it had been whatever it was, it got up to now 7/10 of a volt. This voltage here is 2/10 of a volt, 0.2 volts there, and the story is now switched. With this being 2/10 of a volt and this being 9 volts, there is now a current flowing through R4, charging the capacitor, and then going through this transistor, which is now conducting. So C2 is now starting to charge. The voltage on it is going to be reversing. It had been that at the time it switched, we had a plus to minus 8.3 volts on it. It was plus to minus. Now current is going to be going in this direction, so it's going to overcome that minus charge, and then start charging in a plus to minus direction, and it's going to see, as we're going to see here in just a second, it's going to get up to, or it would be going up to where this would be on the order of 9 volts minus the 0.2 volts. This would be charging toward about 8.8 volts. But once again, because this point is connected to this base, it's not going to be able to get anywhere near that. Because when this gets to be about 0.7 of a volt, it's going to turn this transistor on. We'll talk about that in just a second. In this condition, C1 is now going to be charging through R1 the capacitor on through here to the base. Now we know that base currents are relatively small, and we're going to make this resistance here very small, so there's not going to be enough going on here to cause this LED to continue to burn. The LED is going to stop glowing. This is the off state of it. But there will be a charging of this capacitor, and it's going to head on up to, this is somewhere around 9 volts, this is on the order of 0.7 of a volt. So the voltage on here, plus to minus, will be charging up to about 8.3 volts during this process. So we've got C2 charging this way, heading towards 9 volts. It's not going to get anywhere near that because when it gets to 0.7 of a volt, it's going to cause this to turn on. But while this is conducting, there will be conduction going through here, reversing the voltage on this capacitor and getting it up somewhere around, again, 9 minus 0.7, somewhere around 8.3 volts. Okay, we're now ready. This is growing. The voltage here is growing. We're now ready to see that when this voltage gets up to about 0.7 of a volt, and again, it started down around -8 volts. When this gets up to about 0.7 of a volt, it's going to turn this transistor on. It starts to conduct, pulls this voltage once again to 0.2 of a volt. This capacitor has a plus to minus 8.3 volts on it. It had been 9. When it gets pulled down to 0.2, that's supposed to be a 0.2. 0.2 volts, 0.2 dropping 8.3. This once again then pushes the base voltage here down to about a -8.1 volts instead of the 0.7 of a volt. So at -8.1 volts, it turns this transistor off. So the conduction of this transistor charges the capacitor that then pulls this transistor base up, which turns it on, which then turns this off, and it just goes on and on, back and forth, causing the effect that we're going to see is that this diode will be on when this one is conducting, this one will be on when this one is conducting. And in our actual circuit, we're going to make R3 and R4 be variable so that we can then vary the speed of the flashing, and we'll also be able to vary the duty cycle of them. The duty cycle of the flashing, which means that we'll be able to control how long this light is on relative to how long this light is on.